It's been a few years since I uploaded anything to this channel, but I had an interesting idea for a video series. What I wanted to do was cover some of these papers, if you want to call them that. I mean, I'm not a not a professional or anything like that, but I've had some interesting ideas over the years, such as the mini blockchain scheme being the main one that I might be known for, which was which is the basis for kryptonite, which is a cryptocurrency which you can find at kryptonite.info. But anyway, what I wanted to, well, I've already made a video on that, which is the only video on this channel, obviously, which was about 3 years ago now. But what I wanted to do was discuss some of these other things, make a video on some of these. So a few of these are a bit out of date now. But this negative matter and negative space-time is the one I want to discuss in this video. But if you want to go ahead and read any of these other papers, I might do the ray tracing one next, because that's fairly interesting. But that is a little bit out of date, as I said, and so is the evolving algorithms, because the source code is a lot different to what you will find on GitHub. It's changed a lot since then. My private code, obviously, I mean. I just need to get around to uploading it to GitHub, which I will do. And after this video, I'll also upload some code related to this negative matter stuff, which I'll discuss and which I will show in this video some of these programs that I've made to test some of this stuff. Okay, so here's the paper where I discuss all of this stuff about negative matter and negative spacetime. So basically what it is a zero energy universe with bimetric relativity. That's the idea, and you can see you can read the abstract here. And it's not really my idea, it's not an original idea. It's just one that I find is very little known, even in the scientific community. There's not many people really talking about this idea, despite the fact that it manages to explain a great deal about how the universe works, and things like dark matter and dark energy especially. It tells us a huge amount about what they really are, and they are not at all what we think they are. Very deceptive in their nature, which I think is one of the main reasons why so far we have failed in our searches to find this elusive dark matter particle. So we'll get back to all this stuff and exactly what this is in a minute. But as I was saying, we've had some articles recently showing us talking about how more of these detectors have found nothing in their search for dark matter, and how it's not looking so great for WIMPs right now. From what I understand, they've ruled out a lot of different candidates for the dark matter particle, but not quite all of the candidates, and not even all of the WIMP candidates yet, but just a fraction of them. But it's really not looking good. I like this quote here: "We have to be prepared for the idea that dark matter might not interact with other matter except through gravity." So there was another result recently from this Xenon 1T detector, which is even more recent. This article here is more recent, but that was just because they released the paper related to the results from that. But this detector here is even more advanced, and still it looks like they didn't find anything with this detector either here. And this is a slightly older article, came out back in May. But same thing, it looks like we're not going to find much in this energy range that these devices are looking at. So dark matter particles must be even smaller than previously thought. So basically we just need these detectors need to just keep looking at finer and finer details, or more sensitive and sensitive energy capabilities, detection capabilities. But I think it's important more now than ever to talk about these types of theories, because a lot of people always mention alternative theories such as modified Newtonian dynamics, electric universe, emergent gravity, and so on. But one of the things that you'll never really hear people talk about is these bimetric theories of the universe. Just to sort of illustrate that point, like one of the only videos on YouTube, or one of the only technical lectures on YouTube about negative mass is this one here from this playlist here, Extraordinary Concepts in Physics, which was a one-of-a-kind course taught at Michigan Technological University for credit. The course is aimed at upper-level undergraduate students in physics. However, the concepts involved in the course are easily accessible to everyone. So that's sort of what I want to do in this video as well, is just because I'm not coming up with any original ideas or equations or anything. I just want to sort of give an easy to understand overview of this idea, because I think it's sort of important for people to know about this and understand how it works and all the different really critical problems in cosmology that this model can solve. There's only really one guy who sort of champions this model, this Jean-Pierre Petit. I'm not sure, I probably just butchered his name there, but he's got this brilliant paper which he wrote back in 1995, Twin Universes Cosmology, and of course he's had several papers since then which expand upon this idea, and I believe he now calls it the Janus model or something along those lines. I quite like Twin Universes Cosmology myself. Just a much better name in my opinion. But this paper describes a lot of really brilliant ideas which I'm going to cover, most of them, such as inverse gravitational lensing. Excuse me. And he's just got a lot of neat diagrams here, such as this one I really like. This one in particular is really cool. He's got this no matters land labeled here. So you've got like your galaxy in the center and your anti-galaxy or anti-cluster around it, which is basically the negative matter. And so we're going to get into all that now, and I'll try and make this video as quick as possible. I seem to always rant on and they go on for a long time, this video here is also really good to watch, just to
I'm trying to go through some of the more interesting. It is not
get a basic understanding of what negative mass is and how it behaves, or how it would theoretically behave. I think this is just basic Newtonian dynamics that he talks about here. I haven't watched it in a while, but it's just like an introduction levels thing on negative mass. We're going to get into quite a bit more sort of detail on what negative mass is and how it might behave. So we'll close that now that we don't need it. Close this playlist. And this is a playlist for the Janus cosmological model. If you want to maybe get into a bit more of the detail and math. Anyway, we'll just start off with some basic principles about energy conservation, because this entire theory can really be naturally derived from the logic of energy conservation. Because when we ask ourselves how the universe was created, we really need to think hard about where that energy came from and how it is possible for all the energy in our universe to come from nothing if we assume something like the Big Bang happened where all that energy, even if it began as an infinitely dense point of energy, even if that was always there in some sense, or whatever you want to try to argue, you have to still, energy has to be conserved. You have to explain how it came about without violating, how do you go how do you go from nothing to something, basically, is the question. What we're going to assume is that during the birth of the universe, an equal amount of positive and negative energy was created. And so what we have is a zero energy universe, because the positive energy cancels out all the negative energy. So it's like -1 + 1 equals 0. It's the same concept. All the negative energy balances out all the positive energy. And so energy in that way is conserved through the entire system. And so energy, in some sense, can come from nothing without violating the laws of energy conservation, basically. And so that's our basic assumption that we're going to start with, is that an equal amount of negative and positive energy must have been created during the creation of the universe. Otherwise, it just couldn't happen, right? Even within the framework of quantum mechanics, everything conserves energy always. And so if we assume that during the birth of the universe some sort of quantum fluctuation, right, caused everything to spring from nothing all at once, the only way that could happen without violating some sort of law is that an equal amount of positive and negative energy was created. And even Hawking believed in this concept of a zero energy universe. Anyway, I quite like this video because just because of the quote in it, the thing that Hawking says here, I think is really interesting. Just have a listen to this.
As I was growing up in England after the Second World War, it was a time of austerity. We were taught that you never get something for nothing. But now, after a lifetime of work, I think that in fact you can get a whole universe for free.
And then they just go into
will represent the universe.
To demonstrate how digging a hole is sort of, in a sense, somewhat like negative.
To make
mass,
this hill,
because
he digs a hole in the ground
you're taking,
and uses that soil to build his hill.
Like if you think of the flat Earth as as the lowest energy.
But of course, he's not just making a hill.
The positive mound and the negative mound.
He's also making a hole. In effect, a negative version of the hill.
So that's the basic idea about what negative energy is. So if we believe in this idea that there's an equal amount of negative and positive mass in the universe, what we're saying is that we believe in a zero energy universe. There's a little Wikipedia page here, like an exceptionally small amount of information on this page. Anyway, let's just close some of these tabs that we don't really need anymore, that we've already had a look at. Don't need these detector articles anymore. But the question becomes, if there is such a thing as negative mass in the universe, well, even just negative energy, where is that energy, right? Because Einstein tells us that there's a mass energy equivalence principle, and so if there's negative energy, it should have negative mass, right? And so if something has negative mass, it should have negative gravity. And therefore it should be fairly easy to detect something with negative gravity. The problem is that we've never detected negative particles, any sort of negative matter or negative gravity. Now, there are candidates, some things that we believe do contain or possess negative energy. So, for example, antimatter is the most obvious thing that would probably come to your mind. But most, like, when we're not 100% certain because it's very hard to test, but most of the evidence suggests that antimatter has normal gravity, so it has positive mass. And the other reason why antimatter probably isn't negative matter is because we would expect, if negative matter collided with positive matter, we would expect them to perfectly cancel each other out. If there was an equal amount of positive and negative energy in each particle or whatever, they should perfectly cancel out each other. But that obviously doesn't happen. If antimatter collides with normal matter, it's a huge release of energy. Even so, that is sort of a hint that something might be going on. And we'll get more into that near the end of the video. We'll have another sort of little look at antimatter once we've explained a few more things about all this other stuff. So what are the other candidates? Another popular thing or effect that people often look to is the Casimir effect, because that acts a lot like something which has negative energy, because there's a negative pressure between. If you put two plates really close together, what that will do is restrict the wavelengths of quantum fluctuations that can happen between the plates. So what happens is, outside of the plates there's a higher amount of energy due to more quantum fluctuations happening, and so between the plates there's less fluctuations, and so a lower pressure, and the higher pressure outside the plates will act to push the plates together, and so it's like a sucking pressure that happens and pulls the plates together. And so it's often said that that must be some sort of negative. It's an example of negative energy, because the force is in such a way that the energy between the plates is acting as if it had a negative pressure. But when you think about it, the only reason that is the case is because the normal vacuum fluctuations outside the plates are higher, and so it's all you're getting is a difference in, you're getting a potential which is set up between the outside vacuum and the inside vacuum, and so the vacuum inside the plates is only negative relative to the outside vacuum. It doesn't actually contain any real physical form of negative energy. It's only negative relative to the normal vacuum if you're comparing it that way. But it's just a good way to think about negative pressure, but not an actual real example of negative energy, or something that would have negative mass, put it that way. And so the last candidate for negative energy or negative mass is gravitational potential energy. Now this might seem quite weird at first, but this is the main thing. This is the idea that people like Hawking promote, because what they say is that since the force acting on two bodies decreases with distance, it becomes zero at infinity. Therefore, it makes sense that we should have the energy at the energy at infinity equals zero. The potential energy of a system of two particles or whatever is zero when they are separated by an infinite distance. But once again, this is only a relative difference between wherever you set your 0 point to be, and this is a completely arbitrary choice that we've made to set the energy level at zero at an infinite distance, because it could be that when the two bodies are at a distance of zero, the potential energy is zero, and as I separate them, I put in positive energy into the system, and if I were to release them, that energy would be converted back into kinetic energy as they moved back towards each other. But as I continue to separate them, I'm increasing the potential energy, but the growth in energy decays at the same rate as the gravitational field. And so there's no reason I can't say that or think about it that way. So this is quite similar to the Casimir effect, because it's only a relative difference between two different energy levels, right? A potential energy, that's why it's called gravitational potential energy. It's not a real physical example of negative energy or something that would have negative mass, because obviously it doesn't really make sense to say that a gravity field would have some sort of negative mass. But this is like the mainstream idea of how a zero energy universe could work, is that the potential energy, the negative energy held in all of the gravity fields of all the matter, it perfectly cancels out all the positive energy in all the normal matter. But as I said, I don't really buy into that, and so we're going to take a more literal approach to this, to the mass energy equivalence principle. And we're going to assume that something with negative energy would have a negative mass. And so what we're going to say is that there must be some sort of negative matter. And so what we want to really think about is what would happen in a universe if we started off with a perfectly equal amount of positive and negative matter. So the positive matter behaved the way we know that normal matter behaves, and the negative matter behaved according to whatever model we used for the negative matter. And we will show, I will show two different ways that we can think about that. The more naive way, which is the Newtonian approach, and then we'll look at the more advanced bimetric relativity approach, where we think about things in a bit more complex of a manner. So if we just go back to this paper quickly here, well, first of all, let's just have a quick look at this Wikipedia article here, where it talks about what would happen if we did use just some basic knowledge about Newtonian dynamics and apply it to negative matter. And basically what happens is you get runaway motion, as Hermann, Bondi and these other fellows discovered back in the early days. But basically the rules that we get here is that positive mass attracts both positive mass and negative mass attracts both repels both negative mass and positive mass. So without really thinking about it too hard, what we're really saying is that all the positive matter will, because of the normal gravity, it will clump together, but because all the negative matter will repel all the other negative matter, it sort of remains in this gaseous cloud of negative matter filling space between all the galaxies. Now there is just a bit of a problem, because with those rules, negative matter gets attracted to the positive matter here in the center, which would be, for example, our galaxy here. And the program that I will show sort of near the end of the video will be this simulation program that I used to make this, and also a more recent program that I made, which is like a 3D version of this. If we think about what's happening here, there's a few very interesting things, right? Because as I've got it labeled here, you have this area, the no matters land, where there's no negative or positive matter. And if you think about it, a lack of negative matter is equivalent to positive matter. So taking away negative matter is equivalent to adding positive matter. So because we have this cavity of negative matter around the galaxy, because the negative matter is repelled from it, well, not exactly as I mentioned, but we'll sort that out in a minute. But what happens is you get this cavity, and what that creates is a lensing effect, because the more mass a galaxy has, the more it bends the light traveling around the galaxy. And because taking away negative matter is equivalent to adding positive matter, it seems like there is more mass in galaxies than what there actually is, which describes the overly intense gravitational lensing effects that we observe when we look out at distant galaxies. But the problem here is that the negative matter, as these rules here state, the positive matter does attract the negative matter, and because it clumps up into such a huge ball, a galaxy, it will attract the negative matter. We still get this cavity around it, but it's probably not quite as big as we'd want to explain the dark matter halo. And also the other main critical problem with that is it doesn't help us in any way explain the flat rotation curves that we observe when we measure the velocities of stars and things rotating around the galactic core. Because according to the basic rules of gravity that we understand, the rotation curve, the velocities should fall off with distance, but we sort of see this flat rotation curve with galaxies. So stars at a distance are rotating much faster than they should be, and if there wasn't this sort of invisible mass somehow holding it together, they'd shoot off and then the galaxy would not stay together. So what we really want is a way for this negative matter to be repelled from the positive matter, and for the positive matter to be repelled from the negative matter, so they both repel each other. And the way that we can sort of make that happen is that if we think about it in a bit more of a complex way, and we think about what would happen if we actually did reverse the energy of a particle so it had negative energy. First though, let me just quickly discuss or illustrate an intuitive way of thinking about negative matter. So often gravity is described as this sort of curvature in a space-time fabric. So if we had like some mass here, for example, it would cause like this indentation in the fabric of space-time, and so anything that comes close to this object will fall into the gravitational field. And so that's how we can explain how a planet's able to orbit around the sun and things like that. Everything comes down to this curvature of space-time. So negative mass, instead of creating this downward indentation, what we would see is, because negative mass, remember, has negative gravity, and so it repels things away, and so things roll away from the negative matter. And so this is basically what we get if we apply the basic Newtonian mechanics to negative matter, negative mass. We get these rules where everything is repelled from the negative matter and everything is attracted towards the positive matter. Now, one of the interesting things about the theory of relativity is that nothing with a positive rest mass, with a non-zero rest mass, can reach the speed of light, because as you increase in speed, the energy required grows exponentially, because the mass of the object will actually increase exponentially. And so once you reach the speed of light, the mass becomes infinite. So it's, according to the math, nothing with non-zero rest mass can reach the speed of light. But what if we're talking about something with negative rest mass, right? What would happen then? So this is basically what Jean-Marie, I'm not even going to attempt to pronounce his name, but rest assured, this guy right here is an absolute legend. But through the complete Poincare group of dynamic group theory, he found that reversing the energy of a particle, hence its mass if the particle has one, is equal to reversing its arrow of time. And so the universe, according to general relativity, is a Riemannian manifold associated to a metric tensor solution of Einstein's field equations. In such a framework, the runaway motion prevents the existence of negative matter, which we just discussed. So some bimetric theories of the universe propose that two parallel universes instead of one may exist, with an opposite arrow of time, linked together by the Big Bang and interacting only through gravitation. So recall that quote from earlier from the article where they're saying that it may be something that only works through gravity. This is another hint towards that. And so the universe is then described as a manifold associated to two Riemannian metrics, one with positive matter and the other with negative mass matter. According to group theory, the matter of the conjugated metric would appear to the matter of the other metric as having opposite mass and arrow of time, though its proper time would remain positive. They have their own equations, blah 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 blah. And so we have these new rules now of what would happen. So positive mass attracts positive mass, negative mass attracts negative mass, positive mass and negative mass repel each other. And so these rules are a lot better for what we want here. The only problem here is that negative mass attracts negative mass, which is not really what we want, because we want it to remain in that gaseous type of form. However, there are some ideas about how to deal with negative mass in, well, spaces such as de Sitter space, I believe this article talks about. But they say when they solve the equations for a perfect fluid, it turns out that the energy condition is satisfied everywhere, just as in all other solutions of general relativity that support reasonable universes. So if we think about negative mass or negative matter as some sort of perfect fluid or superfluid, that really helps us solve a lot of problems, or it helps us with the clumping together, because if it did clump together, we would notice these huge negative masses floating around the universe. It's probably not something that we'd miss, and also we want it to remain in that gaseous type of format, because that's the only way that we can explain dark matter and dark energy. So if we don't have that, then we don't really have much at all. So this whole idea of thinking about negative matter as existing in this type of negative space, because if you think about it, positive positive matter is always on the top surface of space-time here, and negative matter is always on the underside, because how can a negative mass exist on this side if it's always pushing the surface up above it to cause things to fall down? So just mathematically thinking about it, they have to exist in these sort of separate dimensions in some sense. So I like to call this side of the surface the negative space, or negative space-time. As we've now learnt, negative matter experiences negative time. So what we have basically is negative matter existing in negative space-time, and positive matter existing in just normal positive space-time, which is what we exist in. So what we get from these new rules, assuming that negative matter is still able to remain in the gaseous type of state, despite the new rule telling us that it probably won't. The reason we like these new rules despite that is because it gives us this opposing forces between the negative and positive matter, which expands the dark matter halo even more, and allows us to explain the flat rotation curves. Because as a positive object, something with positive mass, moves towards the edge of this halo, it's going to experience an increasingly stronger force trying to push it back towards the center of the halo, because of all the negative mass outside of this halo. So what we have here is quite an interesting model, because it explains both the flat rotation curves and the overly intense lensing effect. And it's also quite intuitive, because when you think about it, it makes quite a lot of sense that all the positive matter is going to clump together, and all the negative matter is going to stay separated in this gas sort of state. And then what we get is these cavities around the galaxies, because they still repel each other as well. And we get this very interesting sort of pattern that arises, really. If we go back to this paper, there's a few little diagrams where he sort of shows this cellular looking structure here. And there's also just a great deal of fascinating information in this paper, diagrams about how inverse gravitational lensing works, which is basically what I described with the lensing effect, how that gets artificially increased due to the lack or the cavity of negative matter around the galaxy. And so it's sort of, it's an illusion in a way. There is no real dark matter particle to speak of which creates the effect, the illusion of more invisible mass being there. Assuming this theory is correct, of course. Like, I'm not going to outright claim that it's correct. Of course there could be a dark matter particle, maybe even a WIMP, although I don't have my hopes set very high for that personally, which is why over time more and more I'm starting to lean excuse me, I'm starting to lean more towards these types of alternative theories, especially this inverse gravitational lensing approach. I find quite just elegant and intuitive. Maybe not so much if you don't like the idea of negative numbers. I find a lot of people, the main thing that upsets them about this whole idea is a negative mass. Like, how do you have something like, how do you have an anti-apple or what have you? It just, like, their mind really doesn't like to think about it. And I mean, admittedly, it's extremely weird to think about, but it's not the strangest thing in the world. People took a long time to accept the idea of negative numbers when they were first introduced into number system, because it was just sort of this very unintuitive thing. How do you have something that's negative, right? But mathematically it's completely valid, and it's the only real way that we can explain how something is able to come from nothing without violating laws of energy conservation. Like, how does energy remain conserved if you have an imbalance between the two types of energy, or if you only have one type of energy? You simply can't have conservation of energy. Okay, so the other very important thing that I wanted to mention was that this cloud or fluid of negative matter or negative mass acts as well, it's the reason that the universe would expand, because negative matter has negative gravity, therefore it pushes things apart, unlike normal matter, which has normal gravity and pulls everything together. See, it was once believed that the universe would end in a big crunch because gravity would pull everything together. But then we learned that it was actually expanding, even accelerating. Well, it looks to us as if there's acceleration, but the very nice thing about this cloud of negative matter is that it can explain this elusive dark energy thing, right? Because it does the exact same thing as dark energy is said to do. It pushes everything apart and causes metric expansion, basically. And probably the main criticism against that is, well, it's not constant, because, see, the main theory for dark energy is vacuum fluctuations. And so you create more space, you get more vacuum fluctuations. So the energy level always stays the same. So it's called the cosmological constant. But the problem is, if you add up all the energy from the vacuum fluctuations, you get an answer which is more than 100 orders of magnitude off base. Because we know if there was, the universe would be expanding much faster if vacuum energy was the cause of expansion. So in order the way they basically explain this away is to say, well, there must be some sort of counterforce, some sort of anti-dark matter, which is in itself even more mysterious than dark energy. Sorry, I think I said dark matter. It's more mysterious than dark energy itself, this anti-dark energy. And it requires a completely ridiculous level of fine-tuning in order for the anti-dark energy to cancel out the normal dark energy and leave just the right amount. God damn it. What is this? Don't show again, thank you. Yeah, so it requires a completely ridiculous level of fine-tuning to leave just the right amount of normal dark energy to cause the expansion that we observe, right? It's like something 1 part in 10 to the 60 or something. So this is a much more elegant solution because it doesn't require any sort of fine-tuning. It's just the negative matter is there between all the galaxies, and it causes expansion between all the galaxies. And over time it would get diluted. But the thing is that it would take so long for this to happen that we probably wouldn't even be able to observe it. And there are several theories which says that this could be the case, that it isn't a constant and the value does change over time, but it just takes so long that we can't really detect that change. Okay, so before I finish up by showing some of these simulation programs, one last thing I want to discuss is just the shape of the universe and the origin of the universe, or the birth of the universe. The This whole concept of having an equal amount of positive and negative mass means that the universe has to be perfectly flat. And what that means is it must also be infinite, because a perfectly flat universe will never curve back in on itself. There are some exotic models, geometric models, which have contained flat space but are finite. But Occam's razor would suggest that they're probably less likely to be true than something as simple as just perfectly flat infinite space. That's why a lot of cosmologists tend to like that model and get attracted to it. And also because it's the only model really where energy is conserved. Because you have an equal amount of positive and negative energy, there's no curvature. But if you have an imbalance, there's a curvature, and therefore space is able to curve back in on itself, and it's able to create finite spaces that way. The problem is, if we're saying that the universe began as a singularity containing all of space-time, we have to ask, how can infinite space-time possibly arise from that type of singularity? And this is probably my main criticism of the classical Big Bang theory, is that we just assume that all of this energy decided to suddenly expand from an infinitely dense point, and then eventually over time several complex theories are used to tell us how it arrived at what we see today. So let's just have a look at this video, which is pretty much the only video I could find trying to answer this question.
Many people often ask how the existence of a Big Bang can be reconciled with the possibility that we live in an infinite universe. Many people often ask, wouldn't it take an infinite amount of time for the universe to expand to an infinite size, if all the mass in the universe started out concentrated at one point during the Big Bang?
And then we'll just skip ahead a little bit to where they try to answer this.
Think of all the points in the universe as being arranged in an infinite line. With a certain distance between each point and its two neighboring points. This distance increases with time. If we go backwards in time, this distance decreases. Increases to 0.
So the basic idea here is basically, well, what they're trying to argue is basically, if you have an infinite line of points and then you continuously decrease the distance between each of them, eventually you're going to end up with this single infinite point in the center, apparently. They even show the sides of the line or what have you collapsing into this single point. Now obviously if it's a line of infinite points, there is no end to the points. There's nothing to collapse in, as they show right here. It's just, it just doesn't really make much sense to me. So I don't really buy this idea that one moment it's 0, the space of this singularity is 0, it takes up 0 space, and the next moment it's infinite space-time. As they say here, any time after the Big Bang the distance is greater than 0, but it's an infinite line of points. So how do you go from that one point to then suddenly an infinite an infinite universe full of an infinite number of points or infinite space-time? I just don't see how you can really go from 0 to infinity that easily. Now the reason people are so attached to this idea, despite it seeming so ridiculous or counterintuitive is because most of our observational evidence does suggest that the universe is infinite and flat, or that the shape of the universe is infinite and flat. So the exact shape is still a matter of debate in physical cosmology, but experimental data from various independent sources confirm that the observable universe is flat within only a 0.4% margin of error. Theorists have been blah 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 blah. Arguments have been put forward that the observational data best fit with the conclusion that the shape of the global universe is infinite and flat, but the data are also consistent with other possible shapes, the more exotic shapes which can contain finite space but also flat space at the same time. But as I said, I think we should lean towards the more elegant frameworks, models. I don't really understand why people are so repulsed from alternatives to the classical Big Bang model, this infinitely dense singularity suddenly expanding and then creating everything, or the structure that we see now, using just a really lot of ad hoc mechanisms, in my opinion. But basically, just think about what we're saying when we're saying infinite space-time. We're not just saying that space is infinite, we're saying also that time is infinite, space-time is infinite, and so that would, by definition, that would suggest that time didn't have a start, didn't have an end, and neither does space. So there are other ways that we could possibly think about the birth of the universe. Like, for example, why couldn't it have been just a release of energy inside pre-existing infinite space-time? Like, why couldn't some sort of fluctuation happen inside of pre-existing space-time? If we assume that completely empty, zero energy space-time, we could assume that that's sort of the equivalent of nothing. And there are a lot of arguments that I've made in the past for why I think that is the case, and for why just a completely empty universe which only contains space and time is still equivalent to nothing, even though you have the space and time there. They're just some sort of emergent property of reality itself, like the most fundamental thing that you can have when you've stripped everything else away, basically. But if you get some sort of fluctuation in that space, then you could have a spontaneous release of energy which creates a universe or something like that, as long as it's an equal amount of negative and positive energy released in that event. So basically what this overall model says is that when the Big Bang happened, because there was some negative energy involved in that, and because negative matter travels backwards in time, basically we have like two separate timelines sort of springing off from each other, although it's more sort of parallel to each other, because obviously we can interact with the negative mass, because they both affect this same space-time surface. So if these come close to each other, they can affect each other in using the rules that we have talked about. So another possible explanation for how our universe could have begun is some type of vacuum phase transition, right? So instead of some sort of concentrated release of energy, it would be like an evenly distributed energy throughout the entirety of infinite space-time. Because if some sort of phase transition happened in the vacuum where it changed energy levels and released some amount of energy, or some equal amount of negative and positive energy throughout infinite space-time, it's very possible that that could result in the type of universe that we observe now, like this. With these filaments sort of throughout everything, and then these concentrated nodes of galaxies. Because if the positive matter collapses together, and then all the negative matter remains in this sort of gaseous state, it would very likely produce a structure, a sort of homogeneous structure like we observe when we look out into space. But anyway, I think it's about time to look at these simulation programs that I'm talking about. This first one here is the 2D example, which is shown in my paper, where it's just using like 2D vector forces, and it's just those rules that I discussed. Were here these rules with the arrow of time and energy inversion, where positive mass attracts positive mass, but the only rule I've changed is that negative mass will repel negative mass, just so we get that nice behavior that we want. So let's get this going. And so first, what we see immediately is that the positive mass will get attracted to itself, to other positive mass, and it will fall towards the middle area here, and it will repel all the negative matter surrounding it, and we get this gaseous type formation of negative matter surrounding the positive galaxy type cluster thing in the center. And we also get this nice halo, no matters land surrounding the positive matter. So now let's take a quick look at the more interesting 3D version here. This uses OpenCL, and the kernel is this code here that you can see. Let's just get this going. And so I might have to speed this up slightly if it won't happen fast enough for us. But you can see what will happen is that the positive matter will attract to other positive matter and create these clumps throughout the cube. And I have it set up so that all the matter is contained in this cube so that it doesn't sort of shoot off. Well, at least the negative matter doesn't shoot off. Alright, I just changed the settings a little bit so it'll do what we want a little bit better. But you'll just see the same thing as the 2D simulation basically. All the positive matter will just fall into the middle here and push out all the negative matter, but it just looks a little bit prettier. But you'll notice that everything's contained in this cube here, and that's just sort of to simulate if it was spread through infinite space evenly. Although it's not really the same thing because the forces don't transmit across the sides of the cube, it's just the particles will go out one side and then pop in through the other side of the cube, which is why you'll notice along the edges of the cube here there's little things popping in and out. We'll just move around a little bit here and have a bit of a look at this cluster in the center. This is probably getting about 20 frames per second at the moment, which is one of the reasons I didn't make it more extravagant. I really wanted to have several massive clusters. I mean, I could still do it with this amount of particles, it's just a little bit trickier because you've got to have them spread really far apart and stuff, and I couldn't be bothered doing that at the moment. But this is still very, very pretty, and you can see also, not as well as the 2D example, but you can see that the positive mass in blue, the negative mass in blue is getting repelled away from the positive cluster in the center and creating a sort of cavity around the cluster. Anyway, I think we'll close that for now and wrap it up. I think the only other things that I really wanted to mention was if in this paper near the bottom it just goes over a couple of critical problems that this model helps solve really well, like the cuspy halo problem in particular is a good one. although there's a lot of solutions cropping up recently for how to solve this in other ways. But if WIMPs turn out not to be the solution, then a lot of that could also turn out to be wrong as well. Excuse me. But the cuspy halo problem is basically the problem where our simulations seem to indicate that cold dark matter would become increasingly dense near the center of galaxies or whatever cluster of dark matter we're talking about. It should be the distribution should be denser near the center, basically. So we should get this sort of cuspy halo effect with the dark matter, but we don't see that at all in our measurements, in our observations. What we basically see is like an even distribution, a perfectly even distribution, almost spherical distribution is how we like to model it ideally. And that matches everything that this model tells us, is that there should be this basically spherical cavity of negative matter surrounding the galaxy, which in turn creates the illusion of there being more positive matter, or a spherical halo of positive matter surrounding the galaxy. So that's one really elegant solution that comes from this. Another one is the missing satellite problem, sort of similar thing. A lot of simulations seem to predict that there should be a fair amount of dwarf galaxies, so-called missing satellites, orbiting our galaxy and other galaxies, but we don't see them, hence why they're missing. But obviously this model tells us that there probably wouldn't be anything like that, because it's an illusion. So it's a cavity of negative matter, and there's no real mechanism for that to work. And there's several other things that this paper covers. Cosmic coincidence problem, another good one. An important thing that I forgot to mention about the cosmological constant problem, which is where we measure the vacuum energy to be far too high than what it should be to cause the amount of expansion that we measure, also known as the vacuum catastrophe. What I didn't mention about that was the reason. Well, first of all, virtual particles. What even are virtual particles? We think of those as sort of like random fluctuations in the vacuum, which is why we call it vacuum energy. And these particles are thought to have normal positive mass, but the reason virtual particles are thought to contribute a negative energy factor, even though they have a positive mass, is because they are said to borrow energy from the universe, and so they have some sort of energy debt. But that doesn't really matter for us, because there's also negative fluctuations happening in negative space, right? And so they perfectly, or virtually perfect, they happen in virtually identical quantities. So they basically cancel out all the positive fluctuations are cancelled out by the negative fluctuations, and so that's not the culprit for expansion. Vacuum energy isn't the culprit. The reason is, as I explained, as I believe, is the gaseous cloud or fluid filling space between all galaxies. So that's what this model says is the reason for expansion. And it's not a constant. It does get diluted over time as the negative matter gets diluted. And the other important point is, with this cosmic coincidence problem, we believe that there's an almost identical amount of dark energy compared to all the other normal energy. Although the dark energy is obviously slightly more than the other energy, because it causes expansion. So the robust answer for this is that different parts of the universe could contain different ratios of negative and positive energy. And so we happen to live in a part of the universe where the density of the negative energy is slightly greater than the positive, and that causes expansion. But this cosmic coincidence problem is basically, but why are they so similar? Like, why do they basically match each other if there's only this one precise moment in the universe's age, one precise moment in time where these ratios match as closely as they do right now? Is it just a coincidence that we're observing right now at the right time? And so it's another sort of fine-tuning thing, or whatever you want to call it. But the solution that this model offers does away with all the sort of fine-tuning and just says, well, no, there's just happens to be an identical amount of negative and positive matter, and we just happen to live in a part of the universe where the negative slightly outweighs the positive and causes a metric expansion in the local universe. So I think that just about wraps it up. Obviously, the other solution here that I mentioned was just since the negative energy is spread throughout a larger surface area of space-time, it could somehow exert a larger force, although that seems less legitimate, basically. Before I go, one last thing, guys. I said I'd talk about antimatter briefly. So although there are good reasons to believe antimatter doesn't have negative mass, we're still not entirely sure because it's hard to test, as I said. And although they don't cancel each other out the way we would expect, they still annihilate on contact. And so, according to some theories in particle physics, such as the Feynman-Stuckelberg interpretation, an antiparticle is equivalent to a particle moving backwards in time. So, therefore, it may be worth thinking about the implications of antimatter being negative matter. And also, obviously, the other reason we'd like to frame it as negative matter is because it may help us explain why there seems to be an asymmetry between normal matter and antimatter. And that is quite a big problem for the standard model. So if we can explain that as just, well, there isn't actually less antimatter than normal matter, we just can't detect it because it's all repelled away, or the negative matter is repelled away from the positive matter in our galaxy, so almost none of it will come close to Earth unless we artificially create it in a laboratory. So I think that just about wraps it up now for sure, so I hope you found it enjoyable. I will see you next time.